right, let's get going. First things first, I was getting, please find me a computational project teammate emails as late as yesterday. Does everybody who's sitting here have a computational teammate? No judgments. Does everybody have one? If not, raise your hand so we can match you right now. Okay, good. So everybody has a teammate, so I hope you have started sorting out through the problem. One key thing is you're solving for temperature as a function of r, radius. That radius is discretized in a number of different points, and we have to treat Bax points and still points differently, which is why you have so many NWs and NSs and whatever. Your job is really bookkeeping. All of the equations are given, but you have to sort out what you don't know, what you know, how to label what you don't know, and then form that AX is equal to B, right? Conceptually simple. On paper, it takes quite a moment to do the bookkeeping, and then write down and this is why there are two people for teaching. But essentially, every differential equation that is discretized, okay, is discretized in sort of a similar manner. It could be ordinary differential equation, it could be partial differential equation. I have a discrete version of an operator that takes a point and sort of neighboring points, a few neighboring points, plus minus 1, plus minus 2, that's it. Okay? And sorts out what is a derivative depending on those neighboring points. And that's what gives you that one row in your matrix A that relates a bunch of neighboring unknowns because you're looking for those values, okay, to obey that differential equation. And then there's a whole host of things that you do know, and W, NS, CW, KW, CS, KS, okay? Delta T. Just sorting out in your brain what it is that you know versus what it is that you don't know, and then putting things on paper in terms of equation. Everything unknown on left-hand side, everything known on right-hand side in form 0b. That's your key problem. Not simple. It's not simple to type it in correctly either. So just patience, but that's what your engineering problem is, and that's why you're working in T. All right, just a quick, we are basically done with curve fitting, or last time we were. Just a quick recap. I have some data. Here's some data. There's a bunch of points that kind of form this arc. In order to fit to a curve, what do I need to know before heading into the problem? What do I need to know? Points. That's step one. So I have points. And they're x and y for each of these dots. What else do I need to know? I'm trying to fit it to a curve. What do I have to decide? That's one thing, but basically what it is that I'm fitting to. What is the model? Okay? What is the curve? Okay? Curve is not always a given. The simplest solution is what? The simplest curve ever that you know. That is not even curving. A line. Okay? The simplest curve, the simplest model you ever will fit anything to or you ever will work with is linear. So that's a line. Does that line work well for that data? Any line? Could you find a line? Just sketching it? Be a little difficult. So you gotta change your model. And this, which model am I gonna fit to is part of you. You decide. Computer can try 5 options, okay? But you still have to tell it which 5. These days they're building artificial intelligence to even decide that for us. But until then, you have to be the judge and you have to tell it the model. Great, so here it kind of looks like an arc, it looks parabolic. How do I write down parabolic equation? Well, this is parabolic equation. Y is this function of x with three unknown parameters, a0, a1, a2. Your curve fitting problem is now finding these parameters, a0, a1, a2. So depending on the curve, that's how many unknown parameters you have. You choose the curve. Maybe it's 2, maybe it's 3. It's minimum 2 typically. Okay. And then you go on from there. Okay? Now, if I have 3 unknowns, how do we form? We actually form a system of linear equations looking for these 3. That's what curve fitting does. Now, what am I trying to do? So I'm trying to optimize or minimize difference between my measurement, which is my data coming in, yi, and whatever model I choose. In this case, I have x's playing a role here in terms of a parabola. Right? And I have 3 unknowns, a0, a1, a2. I take square of this difference, residual, I square, and sum up for all of the data that I have. And that's what I'm minimizing. This is how every curve fitting really works. You gotta have a model. I look at the difference or residual between data and the model. Model has a certain number of parameters. How do I get now from this sum of the square of residuals to my equations? What gives me equations? What do I set to 0? There's something I set to 0. This SR is a function of A0, A1, and A2. In order to minimize this, partial derivative, an entire gradient of SR with respect to A0, A1, A2 has to be 0. Similar, like if I had f of x that is parabolic, the minimum is where f prime of x is equal to 0, right? When I translate that to multiple variables, I have to have all of the partial derivatives 0. Okay? That's how minimization works. And this is your very introductory course into optimization and minimization. And a lot of problems come down to this. So what I'm going to do to set up equations for A0, A1, A0, A2, I'm going to take partial derivative of SR with respect to A0 is equal to 1. That's my first equation. Partial derivative of SR with respect to A1 is equal to 0. That's the second. And partial derivative of SR with respect to A2 is equal to 0 is equal to third. And then you work out, the rest is algebra and calculus. Okay? Taking partial derivatives. Don't be surprised if I ask you to set up this problem of equations on your final. Because I want you to know how to solve this class of problems. And then once you have, so if I sort this one out, okay? Once I clean it up, I get that this system of 3 equations and 3 unknowns, and again, everything that I don't know on the left-hand side, everything that I do know on the right-hand side, and it's these sums in terms of the data that I have, xi, yi, I have that data. I know how to compute sums. That was our exam 1. Okay? So all of these sums are really trivial to compute. Maybe a little tedious, but trivial. So I have this 3x3 system. I set up a 3x3 system. We know how to solve a 3x3 system. Any data with any data coming in. Yes? So this is how most curve fitting problems work. Now this is a problem that is linear, and we have some tricks for when these relationships are nonlinear. Taking log of them in some shape or form will give us a linearized version of it. So we just work with the log of the data, or at least log of x's or log of y's, some transformation of it. So we can transform some problems into linear problems, and we did that exercise last time. So I expect you to know that as well. All right. So with that, this is our
curve fitting, which is really an applied solving linear systems, is done, and we're gonna switch to discretizing ODEs. All right. So here's one example where I need to know. So I want to motivate. Why do you need numerical solution to ODEs? You have taken a course that is solving ordinary differential equations, right? And in all of those, you are solving and finding a function that solves an ODE, an actual function that has a form, f of x is equal to something. Okay? That's great, and that works for a relatively limited number of cases. There's a lot of cases where I simply cannot find analytical solution. And in those cases, we need numerical. So in this course, I don't know how good you were in ODEs. Part of me doesn't care, okay? I want you to know how to do it numerically. So I'm not going to test you on how to solve something analytically. There's an entire course devoted to that. And maybe you're taking it right now and stressed out in it. I'm going to take that out of the equation. I want you to learn how to do it numerically. That said, it is important to put the two together because you need to test your numerical solution using an analytical one. Okay? Have to know what you need to get in certain cases where you know the solution. That said, I'm not going to test you on it. Great. So here's one example where I might want to actually solve the numerical solution. So let's say that I have a tank and I have this water flow into the tank that changes some known function. Here it's given as a cosine function, and I have three parameters in these functions that I know that are given. Okay? Regardless, it's pretty complicated, this mass of the water coming in, and it changes in time. Okay? Now, flow out of this is basically limited by the size of the hole at the bottom. Regardless of how it comes in, what comes out is basically a function of the current height. That height changes based on the input, but the function of coming out is the function of basically size of the hole. That's my limit. Okay? And basically it depends on the cross-section of this hole here or pipe and height of the water, because that's the weight. That's what's pushing things down. And of course density. So I have here rho, I have a pipe, I have 2, I have g, this is gravity. What I don't have is this height because it's constantly changing in time. Okay? So as a lot of problems, the way this mass is changing and the way this tank is emptying, which is my engineering problem, emptying tanks is a common engineering problem, is basically it's the change of mass in time is difference between what comes in momentarily and what comes out momentarily at every point in time. Okay? I have a function of how things are changing coming in, so I have this and I have that. Okay? It's just that there's this h of t in there that I don't know. Okay? H. This is a function of time as well. And I can actually change of mass, I can relate it to the height, right? Because there's my mass is rho times volume. And volume is this area of the tank times h of t, right? So basically, change in h in time is related to h itself as well as time itself. And I don't know h. And I might or might not, in this case, this is hard to solve analytically. It will take a moment. But essentially what I have here is that I have a function of time and change dh dt depends both of t and h. Okay? So I have some sort of a function of t and h on the right-hand side. This is sort of a generic type of the problem, generic type of differential equation. And regardless of the, so for some simple cases of this function on the other side, for instance, if this is just a function of t, then I can integrate. I can separate variables and all that jazz. and integrate. But if I have h in there, that becomes hard. Sometimes I can, sometimes I cannot. Again, I'm going to not ask you to do separation of variables and integrate. We're going to do this numerically. Yeah? All right. So basically, I will need to solve this, I will need what is times 0, and then after that, I march in time and solve until some time that I want to solve for. Okay? 1 day, 2 days, I don't know how long it takes to empty this tank. Okay? All right. So differential equations, they kind of are divided into initial value problems. They're time dependent, and this is this example that I've given. Okay? They could be boundary value problems. This is the problem that we solved in terms of the temperature when we had an example of how to formulate a system. The problem you're having in your computational example is both boundary value problem. I have boundaries that are set in space, and I have initial solution in time because it's both in space and time. So it's initial and boundary value problem. And order refers to the order of derivatives that I have. I could have first order if I have only one derivative, or second order if I have two. The problem in your computational project is second order, and this is why it's computational project. That said, we're giving you all of the equations. We're not asking you to discretize. Okay? And it could be also partial differential equations, so I could have multiple variables, both in space, and then there could be additional time. All right. So what we're going to do in this lecture is a special initial value problems where I have dh dt is a function of t and h, or I could have more generally dy dx is a function of both x and y. Okay? And this is going to be the general problem we are solving in this lecture. So the way all of these problems work, okay, is that I'm stepping from a known initial point, and the next point I'm just saying, okay, look at this previous value and decide what it's going to be depending on that previous value. So the simplest thing I could do is this: I have an old value yi, and I'm going to take some slope and step size. Now h is my step size, and I'm going to solve in terms of that step size and slope, and move on, and then go to the next step. Okay? So that is conceptually what I'm working on. So basically what I'm doing is I'm discretizing my space of x's, okay? And I'm deciding how many I have. That's what we always do when we look for numerical solutions. We discretize our space, and we are looking for values at those discrete points. That's it. That's our numerical solution. So our numerical solution is a vector of these values. And how big of a vector? Well, how big computer do you have? So the step size is desirable to be very small. But again, how big computer do you have? If it's too small, you can't solve for it. Okay, great. So I have this, I'm starting from a point. So maybe I started here. So I'm marching in space. So let's say that I have this known initial value that I'm starting from, and then I'm building my solution from there on. So I'm now counting that I have xi, and I have yi from my previously computed step, or from my initial value. So now on the next step, I need this slope to go to, and well, if I'm very accurate, I would go here, but if I'm not very accurate, I'm just gonna do the simplest thing I have always done in this course, is take a derivative, okay? Take the slope of this function at this point. Remember root finding problems? We were taking the slope down to 0. Well, now we're just taking it to the next step. And my f is slightly different. My objective is slightly different, but the system is the same. So we take this slope, and we just take, this is my numerical solution, is this slope, phi. I'm calling it phi here. And I'm just taking this value plus slope times step, which is phi times h. That's my numerical solution. That's simplest thing I can do. Now, what is phi? What is slope? So this is my function y of x. What is dy dx? Look at the slide. What does my differential equation say? What is dy dx? F of xy. And that's my slope. Okay. So my slope, the simplest, will turn also the dumbest, but the simplest thing I can do is take f of xi, yi, that's the slope here, based on how my differential equation is posed. Yes, I know f. In my previous slide, that f was that k1 plus k2 cosine of something plus square root of something else. Okay? Yes? So I can evaluate it. I know how to write the function in Python with two variables. I know how to evaluate it. Yes? Excellent. So that's going to be our simplest thing, and that's called Euler's method. So my slope, dy dx, is f of xi, yi. Okay? So that gives me some predicted value. This slope, now I just inverted things a little. Different function here. That's the function I'm looking for that I actually don't know. But I know the slope at this point, or its estimate, and that's taking me over there. So I have a predicted value, and I have some true value that I know that I don't know that I'm looking for. And this is the error that I'm conceptually making. So at every step, what I have as an error is both this error, well, my true value, my function is actually nonlinear, and I'm linearizing it, right? That's what we always know how to do, linearize things. So there's an error in this linearization that I'm making at every step. And what I'm also carrying as baggage is all of the previous steps, previous mistakes I made before, and previous errors that have piled up until now. So those are my two sources of error in this numerical scheme. Now, if I'm ever linearizing things, what formula gives me the error? Then I just take the linear part and then derivative, first order derivative part. What formula typically gives me? What is the single formula you need to know for calculus? Oh boy, I didn't teach you anything this semester. Evaluation of Dr. Pradanic, bad. Taylor! Yeah, okay, I thought somebody something. All right. So Taylor series gives me evaluation this year. Good news is we're not going to go into this evaluation. That would be beyond the introductory course of numerical analysis. Okay? Okay? So basically, I have chopped off all of those second order, right? If I think about my yi plus 1, it's evaluating value of y of x using a nearby yi and dy dx, right? And then that spacing h, which is yi plus 1 minus yi. Yes? And then I have all those higher order terms that I have conveniently chopped off. And the simple numerical methods always do that. They're really variants of Taylor's formula and how to use it in different ways. So this is the error here between true and predicted value that I chopped off at this point. Okay? So this is how far you could, like if you have really bad step size h, you could you will get generally the true solution's shape, but not necessarily a very good solution. But as your h gets smaller, so this is what you're chopping off, and this is what it can tell you how big error you can do. So generally, your error here is what we say of order h squared. Okay? And as h gets smaller, the error gets smaller too. So here I was stepping too quickly. If I step with smaller step, I'm going to get closer to my solution. Yes? Overall,
I'm making order of h squared here, but then I also have this history of making error, and that sums up to order O of h. Okay? So the higher the order of the method in terms of h, what is my error, the better. Okay? And we will see some methods that perform way better than Euler's method. But this is the error that I make at every step, but that piles up, so overall I get O of h. But this is how it behaves, and we're going to get to looking at this on a particular example. So basically, as I refine my h, I will get closer to the true solution. And the objective, of course, is to hit it right there on the true solution, right? So error analysis, I always have some round off that I cannot avoid. Okay, in computing, the way I'm storing numbers. And I have this, what we call truncation, because we truncated Taylor series, we chopped off a lot of terms in that formula. So there is this local current truncation error, and there is a pileup from history. We call that propagation. It propagates from history. Okay, so those are the sources of my error in any kind of method, including Euler's method. Okay? Is this conceptually clear? Again, we're not going to analyze it, but I just want you to know where the sources of error are. All right. So your global truncation error is combined whatever you're making at the local step, because you're using approximate formula, and then the pileup from history up until to that point. All right. So let's actually do an exercise immediately. I have a differential equation. It's actually a simple one. My dy dx here is only function of x, so I can actually integrate. I'm not asking you to integrate. I'm giving you what analytical solution is so we can compare to it. Okay? But I want you to program Euler method for this problem. Let's go. Open up Python. And before you do that, let's actually just, with a starting point of 0, 0, which is going to be starting point in your program, give me what is the next y1. And for h is equal to 0.5. Using this Euler's formula. So first by hand, so that you know what you need to get. So first compute by hand. So what we are conceptually doing, I have x on 0 to 4. Those are my x's.
Actually, is this very
My h is 0.5, so I have 0.5, 1, 1.5, 2, 2.5, 3, 3.5, and 4. Those are the points where I'm looking for a solution. This is x0, x1, x2, x3, x4, x5, x6, x7, x8. Yes? That's my discretization. Numerically, I'm looking for matching y of x. But numerically, I'm looking for y0, y1, y2, y3, y4, y5, y6, y7.
7, y 8. So my numerical solution is a vector with 9 values that match those x's. If I decrease spacing, it's going to be a larger vector, but it's still going to be sort of a vector approximation of my y of x. Is that kind of conceptually clear? That's what we always do in numerical methods. So we discretize and we are looking for some function at those discretized points. Okay, all I know about y is that dy dx is f of xy, and this f of xy is this polynomial here. Yes? So I gave you a polynomial, I could have given you anything else. Some function of x and y, in this case just a function of x. But what I have to have is this initial point. So what is my x0, y0? On the slide. 0, 1. So I start here. That's given. That's my initial value. This is initial value problem. Yeah? Are we mapping it spatially? Excellent. So starting from this value, I don't know what y is. That's what I'm looking for. But I have a slope, dy dx. What is its slope at this point? Based on the differential equation, what is it? And that is minus 2x0 cubed plus 12x0 squared minus 20x0 plus 8.5. Evaluated at 0, that is equal to? That is my slope right there, f of xi, yi, for current point I. So if I is equal to 0, my y1 is y0 plus slope 8.5 times h. What is h? One plus this 4.25. Questions? Are we mapping our general problem to this particular one? Great. So that's 5.5. Oops, I jumped pretty high up here. That's my predicted value. So that's numerical prediction. What is my actual analytical solution? Where does it say what is an analytical solution? I didn't ask you to find it. I didn't ask you to integrate. It's given on the slide. Where is it? So this evaluated at what point? This point, 0.5, right? Is my analytical solution. Can you calculate the error? Absolute error and relative error. Can you? Absolute error is just the difference. Relative error is the difference divided by the actual true value. If you have the true value, it's given by analytical solution. questions? Is everybody okay with calculating an error? We'll calculate it. So now this h, and how many points do I have to discretize? Those are inputs. Okay? I could give you what my x0 and y0 are. Those are inputs. They change my initial value problem. I could give you what's the endpoint. Do you want to end at 4? Do you want to end at 8? 12? 3? Okay. What is your spacing? Those are the inputs at the beginning of your code. So I want you to write a loop that now steps through and finds y2 in terms of y1, y3 in terms of y2, y4 in terms of y3, y5 in terms of y4, all using this rule up there that the yi plus 1 is yi plus f of xi yi. And then I want you to make a function out of it called Euler method. So first figure out the mechanics of it, then it's easy to put it together into a function, right? Take a picture of this and put it on the slide. Yes?
Do you want the error to be relative approximate? Or
Either. I like relative errors. But that's right now because you know analytical solutions, so you can calculate. You don't always know analytical solutions. But here we evaluate it.
Relative error would be what you get at the first step minus the
True value
divided by the true value.
That's always what relative error is, right? If you know the true value. If not, you work with the best you got. Oh, actually, okay.